Let's cover how to implement some basic data structures. You'll end up doing this more in a data structures class, but it is good to get acquainted with it. Up until now, we've worked with static arrays, whose sizes must be known at compile time, and dynamic arrays, which can be any size, but they're difficult to resize. Working with dynamic arrays means that anytime we want to resize it, we have to make a new array and copy the data over. That could be slow if you have a lot of complex objects in your array. We can write data structures that allow us to add new elements to our list without a complex resize process. Through utilizing pointers and dynamic variables, we can use a pointer to point to the next element of a list, so that we no longer need to rely on contiguous sequence of memory blocks. With a linked list, we will need a list class and a node class. The node class will be each element of the list. It will store the data, as well as the pointer to the next object. Anytime we need a new node, we simply create one and point to it. You could also design the nodes to point to the previous node as well. This would be a doubly linked list. The list object will contain a pointer to the first node, and perhaps to the last node, as well as any functions needed to add items to the list, remove items, and access items. The list does not keep track of every element, at minimum just the first one, but maybe also the last one. To get the other elements, you would have to traverse the list, starting at the first node and going through each node through the next pointer. So let's implement a linked list and see how it works. Okay, so the first thing we need in a linked list is a node. So we'll create a class node, and I'm just going to make everything public. Normally the node should only be used within the linked list, so we can either make the linked list a friend or we could just make this public. Now it will store some sort of data. We don't know what kind of data. I mean, we can make a specific linked list that deals with just strings, but let's use templates. So we'll have template type name T, and we're going to have a pointer to the next node, and I'm going to implement a pointer to the previous node as well. I'm also going to make a constructor, and it will say pointer next is null and pointer previous is null, just so everything's kind of safe when it's first created. So then our linked list class, it will have the node of the very first item, so we'll have to say node of type T. We don't know what the T is necessarily, it's just the template type. We'll have a head and tail, or front and back. I'll just say front and end of the list, and a size. So because node is a template, we're going to have to also make linked list a template. So when we end up adding it in here, we'll declare it just like the standard template library. So linked list. Now, like how vectors would have a string or an int or something like that, we'll have to declare ours the same way. It's a template, a list of integers, and so on. So some of the functionality we need for our linked list, well, I'm going to make this one a pretty extensive doubly linked list, so that we can implement a queue and a struct with this linked list pretty easily. Well, of course, we're going to need a constructor and a destructor first, and I'm not going to implement these at the moment. And I'm defining these inside of the class just to make it a little bit easier on me. Since this is a template, it's better to keep everything in the header file. I'm going to declare a clear function so we don't have to write that functionality in multiple places if we don't have to. We'll have a push back, and we'll pass in some sort of data. We'll have push front, so we can put data at the beginning or the end of the list. We'll have pop back, so we can remove an item from the back of the list, or pop front, so we can remove an item from the front of the list. Okay, and it will also be handy to have a function to get the first item, the first set of data, and the last set of data from the list. And we can also create an at function, so we can make a function that will get an element of the list at some position. We'll also have something to return the size, and maybe something to say is it empty or not. And just to make it easy, let's just have a display function as well. So these are all of the functions we'll have. Let's implement these. For the constructor, let's just set the front pointer to null and the end pointer to null and the size to 0. Here, I'm just going to call the clear function so we don't have to end up implementing that multiple times if we do end up expanding it to ever need to clear the entire list again. So clear should be pretty simple. We'll say while the frontmost pointer, while the first item is not null, we're just going to pop the items off. So we can pop from the front or the back, doesn't matter. And then we'll have to implement these. Let's do the simple ones first though. So these are all pretty small. Int size, return the size. Is empty, return whether m size is equal to 0, so this will either be true or false. Get first, that's just returning the data in the frontmost element, so data. And of course right now this doesn't have any sort of error checking, so you don't want to call get last if the list is empty. We're just keeping it completely super simple right now, just to keep the code very straightforward and easy to read. So we have those. Those would be pretty easy. Let's say that we already have a list and we wanted to display everything in it. I just want to show you how we'd traverse the list real quick. So we would start with a basically kind of just a pointer that points at each element of the list, and we're going to start it at the front if we're just displaying in order. We can have a counter and just display things by their quote-unquote index and say while pointer current is not null, we're going to keep traversing forward. Pointer current is equal to pointer current pointer next, so it'll keep going to the next pointer until it hits the end of the list. We can output the counter and the value. And we'll want to increment counter as well. So this is a really simple way to traverse from the beginning to the end of the list. We have to go through each element's next pointer to do that. We can't randomly access elements like we can with an array. So we don't actually have anything implemented to allow the user to push information onto our list, so let's go ahead and do that. So push back. We're going to create a new node, and we're going to set its data to whatever was passed in. And we'll do the same when we're pushing to the front as well. Now, if the front pointer is null and the end pointer is null, that means there's nothing in the list yet. It's an empty list. Otherwise, we're going to have to add. So here it'd be new node goes to the end of the list. And then down here, this would be similar, except else new node goes to the front of the list. So what do we do if it's empty? Well, the new node is basically our front and end, so pointer front is equal to new node, pointer end is equal to new node, and the same down here. And if we go to if we already have at least one node there, we'll then add this to the end of the list or the front of the list. So if we're adding it to the end of the list, then we'll say new node, and we have a pointer to show the previous. The previous node, new node goes on the end of the list, so the previous would be the current tail, the current end. Then we'll say the current end's next item will be our new node, and pointer end will now point this to the new node because it's the new ending. And down here we'll have the new node next item. The new node will be the new front of the list, so its next will be the current front of the list. Pointer front will set its previous item to the new node, and we'll set the new front to the new node. So now we should be able to push things to the front or the back. Alright, now if we want to pop information, we'll have to say, let's see, if the size is 0, we're just going to return. We don't want to do anything. Not return 0, just return for both of these. Or if the front and the last pointers are the same object, then we only have one thing in the list and we'll need to destroy it and kind of clear it out. So we can say delete pointer front equals null, pointer end equals null, and m size equals 0. So we also have this clear pop back, but that's just going to call this. So this is responsible for handling erasing that information. So down here, and we have else. Otherwise, we're going to remove the last element or remove the first element. So we'll remove the last element. The second to the last element now needs to become the last element. So we'll keep a temporary pointer and we'll set it to the previous pointer previous. So the second to last, we'll delete the current last element. We'll set the new last element to the previous one that we have as temp. And that one is pointing at the old one as the end, so pointer end, pointer next equals null, and m size. So this is the second to the last. It should be pointing to the pointer end, and then pointer end points backwards to this one. We delete the end, we set a new end, and then we also have to make sure it's null. So here we're going to do something pretty similar. We're going to need a temporary variable, but we're going to set it to the first element, the next element after that. So this is the second element. We will delete the first element. We'll update the pointer. And we need to make sure that its previous is not pointing to anything. So pointer front, pointer previous is null, and we'll decrease the size. So let's say we have A, B, C. As an example, we're removing A. A and B are pointing to each other. We delete A. Now B is the new top, but we need to make sure its previous is no longer A. Alright, and then finally we have the at function. So we just have to iterate until we find the node that we're looking for with a counter. I'm going to copy our display functionality at the moment. We have a counter, but instead of ending when we hit the last, when we're out of items, we'll say, well, the counter is less than the index. We're not outputting anything here. We'll keep counting, we'll go to the next pointer, and we don't have any error checking again, just for simplicity, but by the time it gets to that index, as long as the index is, hopefully above 0 and or greater than or equal to 0 and less than the size, we should, at the end of this while loop, have our item. So we can return pointer current data. So that should be all we need to create this list. We have number, we can push to the back, we can push to the front. So let's just do 2, and then we'll do push front. Let's say 20, 21, and 22. Number dot display. So display 1. If we run this, so this was pushed on the back, 10, 11, 12, then we pushed these on the front, so 20 went on the front first, then 21, then 22. We can then also number dot pop back, number dot pop front. So, oop, I have this backwards. So we'll pop back first. Okay, I missed something up here in the push functions. I did not increment the size, so it was always set to 0. So now it should work. So we're pushing these. We're going to pop back, so we popped the last item, and then pop front, we popped the very first item, and so we can see that that works. Alright, now we can use this linked list to make a stack or a queue. A stack is a type of data structure that restricts how new items are added to it, and how items are accessed and removed from it. It is known as last in, first out, because the first item pushed onto a stack will be the last item to be removed, and likewise, the most recent item added to the stack will be the first item to be removed. You can implement a stack with a simple array or on top of a linked list. To add a new item to the stack, we will have a function called push. To access the topmost item from the stack, we will have a function called top. And to remove the topmost item from the stack, we will have a function called pop. Let's modify our linked list and turn it into a stack. So now that we have the hard part out of the way, making a stack is pretty easy. So I've included the linked list object. We're going to create a stack. And since the stack is a template, we'll also, or the linked list is a template, we'll have type name t. Let me see if I can, what is the thing? Folding? Fold all? I don't want it that folded. Okay, so we can see all of the functions in the linked list. So, for the stack, we're going to need a push. We're going to need pop. We're going to need the top value. And maybe even the size. And then private, we'll have the linked list. Let's just name that list like that. So we'll need to implement all of these. This will be pretty easy. We can say container dot, or sorry, not container, mlist dot push back and the data. So we've already implemented push back and push front. All we have to do is use the stack in the way that it's supposed to be. The where you have a list of things. So the very first item goes on the bottom, the next item, next item, next item, next item. So we are essentially pushing to the end of the list, and we're only going to be popping from, wait, do I have that right? Popping from the end of the list. So we push, okay, yeah, we push, it becomes here, then the last, let's say this is the last item, and then that will be what we get back. Okay, dot pop back, and we'll just get the top item. I'm going to add some couts just so we can kind of keep track of it. So pop the top value. Let me minimize that over on that side. Then over here we'll just say push the data. Now the top, we're just going to get whatever the data is of the last item. So we have get last, and we can return the size. So if we go back here, I'm going to erase all of this, or let's say stack number. We're going to need to include a stack, and let's remove that. Let's just have a for loop. For int I is 0, I is less than 5. Let's just say number dot push, and we'll just push some numbers on there. And I'll add a label, and then we'll pop just to see the order that it goes in. So while number dot size is not 0, we're going to keep popping numbers off the stack. So pop. Now if I run this, it's pushing 0s and 3, 6, 9, 12, and it is popping them off in the reverse order. Okay. A queue is another type of data structure that restricts how new items are added to it and how items are removed and accessed from it. It is known as first in, first out. It is like queuing up in a line at the store. The first item into the list will also be the first item removed from the list. We will have a push function to add a new item to the end of the structure. To get an item at the front of the list, we use the function front. And to remove an item at the front of the list, we use the function pop. Let's modify the linked list to make a queue. So, the queue is also pretty easy. We'll go ahead and go here, we'll create a queue. It will be a template. It'll be very similar to the stack. I'll copy this over for now, except instead of top, we'll have the front, and we're going to have to get the first item. When we pop, we're going to pop from the front, but we can still push to the back. So everyone's lining up at the back of the list, but the person at the front of the list gets to go first. Otherwise, this is pretty much the same. So if I change this, let's just say we have queue, we'll just name this queue. No, that's a data type. Let's just name this my queue and my stack. So we'll repeat the same things. We'll say push to stack, pop from stack, and then we'll do the same thing with the queue so we can see them both. Pop from queue, push to queue. So run, I didn't include the queue. Run, and then that one. Okay, this is front. It's going to get the front item. Okay, so what I did is I had top here just to output the label for the topmost item, but that was for the stack. This is the queue. We need the frontmost item. So push to stack, then reverse order, push to queue, and then it comes out in the same order that it was entered in. So those are basic data types. It is good to know how these data structures work. However, the standard template library has implementations of a lot of the structures that you would need to use. It is good to practice writing your own data structures, but if you're working on a project, I'd suggest just sticking with the standard template library.